today we're going to do October-November 2024, paper 41. Okay, that's paper 4, alternative to practical, variant 1. A teacher investigates the electrolysis of molten lead-2 bromide. Lead-2 bromide is a solid at room temperature, right? It's an ionic compound. Figure 1.1 shows the apparatus that the teacher uses. Name the pieces of apparatus labeled L and M. Okay, so L and M are electrodes, right? L and M are electrodes, right? We've got the cathode, which is negative. That's where cations go, positive ions, right? And we've got the anode, which is positive, right? That's where the anions go, right? So name is electrode. And the material they're made from is graphite, right? Or carbon. You can also use platinum. Okay, but generally graphite is preferred because very high melting point. Okay. And obviously not as expensive as platinum. Describe the appearance of the products at L and M. Okay, so at L, again, you're going to get lead, right? If you're doing molten ionic compound at the cathode, you're going to get the metal, right? Cation, Pb2 plus lead. Ions will form lead metal, right? That's Pb. Okay, it's a gray, yeah, silver metal, right? So product at L will be shiny gray or solid silver, right? Shiny gray or silver solid. Okay, lead is a bit darker in color, it's more grayish. And then at M, we're going to see bromine gas form, right? Because bromide will form bromine gas, right? Bromine is a liquid at room temperature, but when you're doing electrolysis, the temperature is high, so you're going to get bromine gas, and that's going to be an orange gas or brown gas of bromine, okay? Orange or brown gas, all right? Bromine gas. The teacher stops heating and allows the lead-2 bromide to cool. Explain why the lamp goes out. Okay, so we've got a lamp here. When you allow the molten bromide to cool, it turns into a solid. And once it turns into a solid, it can't conduct, right? Because solid ionic compounds can't conduct. So when it's hot, it's melted, right? It's melted, it's molten. It's in liquid form, right? But you need to maintain a high temperature because ionic compounds are very high melting point. If you allow it to cool, it turns into a solid and therefore it cannot conduct, right? So we can say that lead-2 bromide turns into a solid, right? Hence, ions are no longer mobile, right? Are no longer mobile, and current cannot flow, okay, because they cannot carry charge anymore. Okay. A student titrates 4 samples of 0.8 mole per dm cube aqueous sodium hydroxide with aqueous ethane dioic acid. In titration 1, the student rinses and fills a burette with aqueous ethane dioic acid. Okay, so your burette has ethane dioic acid, and use a volumetric pipette to add 25 cm cube of NaOH to a conical flask. Okay. Adds thymophthalene indicator to the conical flask. Places the conical flask on a white tile. Adds aqueous ethane dioic acid from the burette while swirling the flask, adding drop by drop near the endpoint until the solution just changes color. The student repeats the titration 3 more times. Figure 2.1 shows the burette readings for 2 of the titrations. Record the burette readings in table 2.1. Okay, so we just have to read the volume, okay? For titration 1, our initial volume is 0.2, right? Because if you notice on the scale, this is 1, this is 0, so each marking is 0.1, right? If something like this is given, right? If you get something like this, guys, read the meniscus, okay? Read the curved part, okay? The bottom part, not this part, okay? And if it's like an upper meniscus, which doesn't show up anymore, like, but for liquids like mercury, you have an upper meniscus, okay? For liquids like mercury, you have an upper meniscus. Meniscus is just this curved thing, right? So you're always going to read the curve, right? If it's facing upwards, then you're going to read the upward face. For water, it's going to be facing downwards, so you're going to read the downward face, okay? So this is 0.2. That's the initial. And the final is 21.1. The volume used is the difference, the 21.1 minus 0.2. That would be 20.9. Okay, then in titration 2, the initial is 21.3. The final is 41.1234567 41.8. Find the difference between them. That would be 20.5. For titration number 3, they've already given you the final volume used, right? So that means the initial must have been 0.0. Okay, make sure every value is written to one decimal place. Don't just say 0. Okay, say 0.0. Okay, so 20.1, again, this is just this value minus this value, right? And then we have 40.4 minus 20.5, that is 19.9. Okay, now the best titration results are the readings that are closest to each other. Okay, so you only need to, whenever you do a titration, you need to do 2 titrations. You need to pick 2 titrations that are very close to each other. Okay, you need to have 2 titrations that are very close to each other, usually within 0.2. Okay, for the O level or GCSE syllabus, there has to be within 0.2. Okay, for a good result. So these two are a good result, right? Because these two are only 0.2 apart. Okay, so these are your best titration results. Okay, so we've ticked the 2 best titration results. Use the ticked titration results to calculate the average volume of ethane dioic acid needed to neutralize 25 cm cube of the aqueous sodium hydroxide. Okay, so we're going to take 19.9 plus 20.1 divided by 2. That gives us 20.0 centimeter cube. Okay, we just have to find the average. So just add them together, divide by 2, you get 20.0. Okay, don't say 20, again, give it to one decimal place the way it's given. Okay, so 20.0 centimeter cube. Calculate the number of moles of NaOH in 25 cm cube of 0.8 mole per dm cube NaOH. Number of moles is just concentration times volume. Concentration is 0.8. It's in moles per dm cube, so volume is 25 over 1000 decimeter cube, right? To convert from cm cube to dm cube, this comes out to 0.02 moles. 1 mole of ethane dioic acid is neutralized by 2 moles of sodium hydroxide. Use your answers to C and D to calculate the concentration in moles per dm cube of ethane dioic acid. Okay, so we want to find the concentration. Okay, so the first thing we're going to do is we're going to find the moles of ethane dioic acid, right? We have the moles of sodium hydroxide. Okay, we have the moles of sodium hydroxide that we use in the titration. So we can say, the question says that we have acid, we have NaOH, right? It says 1 mole of acid requires 2 moles of hydroxide. So that's the ratio. 1 mole of acid requires 2 moles of hydroxide. We know we have 0.02 moles of hydroxide. So how many moles of acid do we have? Cross multiply, you get 2n is equal to 0.02. That gives you n is equal to 0.01 moles of acid. Okay, we have 0.01 moles of acid. And then we want to find the concentration. We know the volume of acid used on average. We know the volume of acid used is 20 cm cube, right? So the volume of this is 20 over 1000, which is 0.02. So the concentration is number of moles divided by volume, which is 0.01. That's the number of moles of acid divided by the volume in decimeter cube again, because we want moles per dm cube. So divided by 0.02. Okay, and we get the concentration as 0.500 moles per decimeter cube. Okay, we're getting it to 3 significant figures. Okay, because everything is given to 3 significant figures. This is to 3 significant figures, and the sodium hydroxide volume and concentration is to 3 significant figures. Okay, So the concentration of acid comes up to 0.5 moles per dm cube. The formula of ethane dioic acid is this: C2H2O4.NH2O. 100 cm cube of the aqueous ethane dioic acid contains 6.3 grams of this guy. Okay, 100 cm cube contains 6.3 grams of this. Use your answer from E to calculate the relative formula mass of this guy. Okay, so first of all, we have to find the moles. Remember, this is a mole calculation. The general idea for mole calculations is you find the moles of the unknown quantity. We need to find the moles of this guy, right? We're given the mass, we don't know the MR. We have to find the MR, right? So to find the moles, what are we going to do? We have the volume. We have the volume and we have the concentration from the previous part. Okay, we have the concentration from the previous part. Yeah. So we have the volume. Okay, let me say this again though. So we want to find the moles, right? The moles is concentration times volume. We have the volume given to us, and we have the concentration from the previous part, which is 0.5 moles per dm cube. So this is 0.5. That was the concentration times the volume, which is 100 over 1000. So we get 0.05 moles, right? And then we need to find the MR. We're given the mass. We know number of moles is mass over MR. We can rearrange this, right? Get the MR to the left and get the N down. So we get MR is equal to number of mass divided by moles, which is 6.3 divided by 0.05. So 6.3 divided by 0.05, and we get 126. Okay, so that's the MR, 126. Then use your answer from F part 1 to deduce the value of N. Now this whole thing has an MR of 126, right? So we have 2 carbons, which is 2 times 12. We have 2 hydrogens, which is 2 times 1. We have 4 oxygens, which is 4 times 16. Okay, the atomic masses are given to you in the question. And we have N waters, right? We don't know how many waters we have. Water is 18. 16 plus 2 hydrogens, right? 1 oxygen is 16, and then 2 for the hydrogen, so 18. So we have plus 18N is equal to 126. Okay, is equal to 126. So all we got to do is we have 24 plus 2, which is 26, plus 64, which is 90, plus 18N is equal to 126. So 18N is equal to 36. So N is equal to 2. State why the conical flask is placed on a white tile. Okay, the reason we place it on a white tile is to see the color change from the titration, right? Because titration, what happens? The indicator changes color, right? The indicator changes color, and you want to be able to see that color change. So you use a white tile. Okay. So the reason why is to clearly see the color change, right? At the end point. State why a measuring cylinder is not used to measure 25 cm cube of sodium hydroxide. We used a volumetric pipette, right? So it is not accurate enough, right? Or not precise enough. Okay, a burette is much more precise. A burette, sorry, and a pipette, the volumetric pipette is much more precise, so that's why we use it. A student investigates solid Y and solution Z. Solid Y is a white powder. The tests the student does on Y are shown in table 3.1. Some of the observations for these tests are also shown. Okay. So first, dilute acid is added to Y in a boiling tube. The gas produced is tested using lime water. Lime water becomes milky. So when we add dilute acid to Y, the solid dissolves. Okay, the solid dissolves, you get a colorless solution, and then a gas is produced that turns lime water milky. So what gas is that?
Carbon dioxide.
Yes. So if lime water turns milky, it must be carbon dioxide, which means that the compound Y is a carbonate. The compound Y is a carbonate because carbonates react with acids to form carbon dioxide, which turns lime water milky. Okay. Now you can use the table given, okay, but oftentimes you're going to have a hard time finding the exact thing that you're looking for. Okay. So what you'll have to do is first you're going to say, okay, carbon dioxide turns lime water milky. That's you're going to find it here. Turns lime water milky. So that's carbon dioxide. And then you would have to go to the cations and anions table, and you realize if you go to the anions table that carbon dioxide is produced. Okay, so you'll have to find this in the exam. Okay, now finding this is going to be painful at times. Okay, especially if you're short on time, which shouldn't be the case but could be the case. So it's always good to just know these tests, just like because you have to know them anyway for the theory exam. All right, so that means that compound Y has carbonate ions, right? Compound Y has carbonate ions. Dilute nitric acid is added to some of the solution from test 1, then aqueous barium nitrate. You get a white precipitate. Okay. So nitric acid is added to the solution formed in test 1, right? And then you're adding aqueous barium nitrate. Okay. Which means that, so if you're getting a white precipitate with barium, it means that sulfate ions are also present. Okay. Sulfate ions are also present. Okay. That's why we're getting a white precipitate with barium. Yeah. The white precipitate is barium sulfate. Okay. Again, this is a test for sulfate ions. You'll have to find barium nitrate right here. Okay, barium nitrate is used as a test for sulfate ions, right? You add nitric acid and barium nitrate. Okay, you add nitric acid and barium nitrate. So nitric acid and then barium nitrate. Okay, and the observation is also given to you. The observation is that you see a white precipitate. Okay, so it's harder to find if the ion is already given, then it's easy to find the test. But the other way around, if the observations are given, okay, it's harder to find the ions, which is why it's just better to know them. Okay, all right. Add aqueous sodium hydroxide drop by drop to some of the solution from test 1 until a change is seen. Then add excess aqueous sodium hydroxide. So you see a white precipitate that's soluble in excess. Okay, white precipitate that's soluble in excess. Now the white ions, if you guys remember, are ZAC, right? Zinc, aluminum, calcium, right? Zinc is soluble in both, right? Zinc is soluble in both excess hydroxide and excess ammonia. You get a white precipitate that's soluble in both. Aluminum is soluble in hydroxide but not in ammonia, right? Calcium is not soluble. This is soluble in hydroxide, so it must be zinc or aluminum. It must be zinc or aluminum. Okay, but it's also soluble in ammonia. So that means it's zinc. Okay, that means it's zinc. Okay. So that means zinc ions are present. Okay. Zinc ions are present because zinc is the only cation that forms a white precipitate with ammonia and hydroxide, and it's soluble in both. Okay, and you can verify that from the table. Okay, zinc forms a white precipitate with hydroxide and dissolves in excess, and it forms a white precipitate with ammonia, right, and dissolves in excess. Okay, describe how the gas is passed through lime water in test 1. You may draw a label diagram to help answer the question. So the gas is bubbled through.
Can we write effervescence?
क्या बोल रही
I'm saying the effervescence लिख सकते हैं part 1 में.
नहीं. It's not about how what the observation is. It's about how we pass it through lime water. Let me explain. Okay. The gas is bubbled through lime water. Okay. Using a delivery tube. Okay. So basically what you have here is one way to set this up is basically you can take a tube. So you have your reaction taking place in a flask, and you can take a tube and pass it into, let's say, a test tube or something like that that contains lime water, right? And you can just like take the tube to lime water. Yeah. This is a delivery tube. Okay. The delivery tube is basically taking the carbon dioxide gas into lime water, and then you're going to see the formation of a white precipitate. The lime water will turn white, okay, because calcium carbonate is forming. Okay, so that's how you can test for carbon dioxide. Describe two other observations the student makes in test one. So
Lime water turns milky.
like how I've already. Now, when you're adding a solid, right, if you're getting a colorless solution, it means the solid is disappearing. The solid disappears, right? Solid disappears. And because carbon dioxide gas is because carbon dioxide gas is being produced, you're going to see effervescence. Okay, so those are your two other observations. So the solid dissolves, right, or disappears, right, and you're going to see effervescence of a colorless gas. Okay, because carbon dioxide is being produced. Okay, identify the gas produced in test one. We've already done that. It's carbon dioxide. Okay. When it says identify, you can name it or give the formula. Y contains one anion. Use the observations from test one to identify this anion. So the anion present is observation from test one. We determined it was carbonate, right? Because it's giving carbon dioxide. So CO3 2 minus. Again, if you don't remember the formula, you can just give the name. Okay. Carbonate. And the dilute acid used in test one. The dilute acid used in test one. The dilute acid used in test one is sulfuric acid. How do we know that it's sulfuric acid? Because we took the solution from test one and added barium nitrate, and we saw the white precipitate form, which means sulfate ions were present. Now, why were sulfate ions present? Because we must have added something in the first test that had sulfate. What acid would have sulfate? It would have been sulfuric acid. So initially we had carbonate, right? The anion we had was carbonate, the cation we have is zinc, right? But because we added an acid in test one and used that same solution for test two, that acid that we added must have been sulfuric acid. That's why we got a white precipitate with barium, okay? Because sulfate ions were present in test two, okay? So the acid used is sulfuric acid, H2SO4. Again, you can give the name as well, okay? Identify the cation in Y using the observations from test 3 and 4. That was Zn2 plus, okay? Solution Z is colorless. The student thinks that Z contains copper 2 ions. State why the student is not correct. Because copper 2 ions form a blue solution, right? It says the solution is colorless. Okay, so copper 2 aqueous solution is blue. Okay, solution Z contains potassium ions. Describe how to do a flame test on the solution. So you dip the nichrome wire. Okay, even if you don't remember the name of the wire, it's fine. Okay, you use a wire. Basically, you can just dip the wire into the solution. Okay, and hold in a blue Bunsen flame. Okay, okay, hold in a blue Bunsen flame. And for potassium, we're going to see a lilac flame. Okay, okay. For potassium, we're going to see a lilac flame. All right, the flame color is given to you. So a lilac flame would be seen like a pinkish flame. Okay, confirming the presence of potassium ions. Okay. Solution Z contains ions of a group 7 element. Describe a test and the possible results to identify which group 7 ion is present in Z. So for group 7 elements, okay, for group 7 elements, right? Or for group 7 ions, right? For group 7 ions, right? What do we use? We use dilute nitric acid followed by silver nitrate. Okay, that's given over here. Group 7 ions, right? For all of them, we use dilute nitric acid and then add silver nitrate. Dilute nitric acid, add silver nitrate. Yeah. So what are we going to do? We're going to add dilute nitric acid followed by aqueous silver nitrate. Okay. And then the observations, it says we have to describe the possible results. Possible results mean any of the possibilities. You would see a white, cream, or yellow precipitate, right? Which would confirm if it was white, it would be chloride. If it was cream, then it would have been bromide. And if it was yellow, it would have been iodide. So a white, cream, or yellow precipitate would be observed. Argentan is an alloy containing only zinc, nickel, and copper. Zinc and nickel both react with dilute hydrochloric acid. Copper does not react with dilute hydrochloric acid. Plan an investigation to find the percentage by mass. Okay, so this is the objective. Okay, this is the objective of the investigation. Plan investigation to find the percentage by mass of copper in a powdered sample of argentan. Your plan must include the use of common laboratory apparatus, argentan, and dilute hydrochloric acid. No other chemical should be used. Your plan must include the apparatus needed, the method to use, and the measurements to take, procedures to ensure that the percentage determined is as accurate as possible, and how the measurements are used to determine the percentage by mass of copper in the sample. You may draw a diagram to help answer the question. Okay, the diagram is optional. You do not have to draw the diagram. Okay. So the first thing you do is, generally speaking, okay, whenever you want to dissolve a solid in an aqueous solution, okay, we're going to use a beaker. Okay, so, and because we want to determine the percentage by mass of copper, right, we need to measure the mass of the initial solid. Okay, so what we're going to do is we're going to react the solid. Okay, we're going to react the solid with dilute hydrochloric acid first, right? So what I'm going to do is I'm going to weigh. Okay, I'm going to weigh a fixed mass, okay, of argentan, okay, using a mass balance, okay, using a mass balance or an electronic mass balance, okay, and I'm going to transfer the solid to a beaker, okay. Okay. Now, one thing I want you guys to keep in mind here is that we want to determine the mass of copper, right? Now, when we add hydrochloric acid, the zinc and the nickel will react. They'll dissolve in the acid. Okay, the zinc and the nickel in the solid, right? Once we add acid, the zinc and the nickel will react. Only copper will be left. And then what we can do is we can filter. We can filter, right? We can filter, and we're gonna be left with the filtrate, right? The filtrate is gonna be copper. That's the solid, right? The solid that's left behind is a residue. Okay. We're going to filter, and we left with the filtrate, which is the solution. Okay, we're left with the filtrate, which is the solution, and we're going to be left with the residue, which is the copper, right? And then we can weigh the copper, right? We can weigh the copper. And then from that, we can determine the percentage by mass of copper. We can do mass of copper divided by the initial mass of argentan times 100. Okay, so that's how we determine the percentage. So I'm going to transfer the solid to a beaker, and then we're going to add an excess. Okay, we're going to add an excess of dilute hydrochloric acid. Okay, dilute hydrochloric acid. Okay, we add an excess to ensure that all the zinc and nickel reacts. Okay, we add an excess to ensure that all the zinc and the nickel reacts. Okay, and then so we add an excess of dilute hydrochloric acid. Okay, and then filter to remove the copper, right? To remove the copper. Yeah. Now, once we have the copper, so again, let me explain what we're doing here. We're taking a beaker, okay? We're reacting, and we have the solid, okay? We have the solid, right? And we have the acid, okay? We're reacting the solid with an excess of acid. So whatever does react in the solid completely reacts, like nickel and zinc, right? Then what we're doing is we're filtering, okay? We're filtering, right? We have filtrate. Filtrate is the solution. The zinc and the nickel dissolve. The zinc and the nickel dissolve in the acid. They're obtained in the filtrate. And the leftover solid is copper. Okay? The leftover solid is copper. We can determine the mass of copper. And from the mass of copper, we can determine the percentage, right? So we filter to remove the copper, okay? And then we're going to wash and dry, right? Wash and dry the copper, okay? Because we want to make sure that all the solution is washed off the copper, and we want to make sure that we dry so that we don't get the mass of water, right? So wash and dry the copper and weigh it, right? And then to determine the percentage, right? That's going to be the mass of copper that we get divided by the initial mass of argentan times 100. Okay, and that will give you the percentage by mass of copper. Okay, and then once you're done with that, right, you should repeat the experiment. Okay, you should repeat the experiment. Okay, and take an average. Repeat the experiment, right, and take an average and find the mean. Okay, so repeat the experiment and find the mean of the two percentages obtained. Okay, so let's say in the first trial we got something like 20.2%, and in the second trial, let's say we got something like 20.4%. We can take the average and say that the mass was 20.3%. Okay, more investigations will make it more reliable. Okay, so repeat the investigation or repeat the experiment and find the mean of the percentages. Okay, and that will give you the percentage by mass of copper in the argentan.